Hello students, welcome you all to another new session on diode applications. Okay, so today's topic is clampers. Now in the last two sessions we had discussed in detail about clippers, how do they work. So today we shall be discussing about clampers. Okay, well, lot many students do say that the concept of clampers is a little difficult and confusing. Well, let me assure you that after this particular session you will be able to solve any clamper circuit on your own. You will be able to analyze it on your own. Okay, so without wasting time, let us try to understand what a clamper circuit is. Well, as per the definition, a clamper is nothing but a network which comprises of a diode, a resistor and a capacitor. Okay, so this capacitor is a very important component in clampers, right? So basically what does a clamper do? Well, as per the definition, a clamper shifts or clamps the particular applied signal either in a positive way or in a negative way, which we call it as a DC shift. Okay, so based upon whether the output has been clamped in an upward direction or in the downward direction, we call it as positive or a negative clamper respectively. Okay, so let us try to understand it again in detail. Now say for example, my input signal is a square pulse, okay, whose peak voltages are plus 5 to minus 5 volts. Okay, so that's my input signal. Now if I am applying this particular input signal to the clamper circuit, then what should be the output? Okay, well, first of all there must be clamping. What does clamping mean? It is a DC shift. DC shift. So either the DC shift is in a positive way or in a negative way with respect to the reference level of the input signal. Okay, now at the output side, the output could be like this. Now suppose if this is a positive clamper circuit, then the output could be like this, with the reference levels like plus 10 volts, 0 volt, plus 5 volts and 0 volts. Okay, so here this is positive clamping and the output signal has got clamped by plus 5 volts, because here it is 0 to plus 5, 0 to minus 5, and at the output side it is from 0 volts to plus 5 and plus 10 volts. Okay, now one important thing to be observed in this case is, especially with respect to the clampers, the appearance of the output signal has not got changed when compared to the input signal. The appearance is the same. That means the magnitude is also the same. Okay, overall the magnitude is 10 volts. In this case it is 10 volts overall magnitude, and at the output side also the magnitude is 10 volts. The only thing is that there is a DC shift. Now we'll have to understand how does this DC shift occur. Okay, the DC shift can happen in a positive direction or in a negative direction. Now how does it occur? Let us try to understand. So we will draw the simplest clamper circuit first and try to understand the shift that happens with respect to a clamper circuit. Okay, so well, as I had already mentioned, a clamper circuit consists of a capacitor. It consists of a capacitor, a diode, and a resistor. So these three are the components which are present in any clamper circuit. Okay, so C is the capacitor, D is the diode, and R is the resistor. Okay, now let the input signal be a square pulse which is continuously varying with respect to time. So let me call it as Vi. The voltage levels being plus 5 volts to minus 5 volts. Okay, fine. Now we will have to note down one or two important observations here. The first observation is that in the case of a clamper circuit, the capacitor is exactly in between the input signal and the output. So the output is across the resistor. Okay, so the capacitor is connected in between the output and the input and the output, while the diode and the resistors are in parallel with respect to the input signal. Okay, the diode and the resistor are in parallel with respect to the input signal. Okay, so we'll have to consider this particular point. And the second point is related to the time constant. Usually we denote it as tau. The time constant tau is the product of R and C. Okay, we'll have to assume that the time constant tau is sufficiently large enough when compared to the discharging time of the capacitor when the diode is off. Okay, so this condition should also be kept in our mind. Okay, now how do we start analyzing this particular clamper circuit? The most important step 1 is that you will have to consider that cycle of the input signal which forward biases the diode. Okay, because when the diode is forward biased, the capacitor has charged. Else, if the diode is reverse biased, then we cannot start analyzing the clamper circuit. So we'll always have to start analyzing the clamper circuit when the diode is forward biased. So that particular cycle of the input should be considered. Now in this case, during the positive half, the diode will be forward biased. Okay, so let's try to understand. During positive half of the input signal, so when I say positive half, this is plus, minus. Okay, so because that is the capacitor gets charged. Okay, this plate gets charged to the positive charges, whereas the negative plate gets charged with the negative charges. Now because you have a diode, we'll consider it to be a silicon diode. The drop across the silicon diode is 0.7. Okay, so let me just keep it as silicon diode with a drop of 0.7. So a silicon diode, the drop is 0.7 volts. So we'll have to make that assumption. Okay, fine. Now at the output side, so we'll have to understand it in a similar way as we had understood the output for a clipper circuit. Okay, which means input and then subsequently the output below the input signal. So we'll be doing the same thing. Let me draw the input again with the defined voltage levels. 5 volts. This is minus 5 volts. Now at the output side, now we'll have to understand what is the transition level. Okay, In this case, plus minus. Okay, so now this particular line is in parallel with respect to the input loop. Okay, so this has to be considered as a separate entity. So it is plus 0.7 volts. So the transition level is plus 0.7 volts. Now again, let me repeat that. Marking the transition level or the voltage at the output side is extremely crucial, okay, because that actually holds as the benchmark from where your output can be drawn properly. Okay, so if something goes wrong in identifying the transition level voltage, then the output waveform, especially the voltage levels, will go wrong. Okay, so we'll have to take care of that. So in this case it is plus 0.7 volts. So that's my transition level voltage. Okay, fine. Now during the positive half, the diode is on, right? So when the diode is on, that means I have a path like this. Okay, so that I can apply KVL. Now let me apply KVL to it. Okay, so that's my input VI. Next, so this is voltage across the capacitor, which I denote it as VC. So this is plus to minus, that means it is minus VC. Then again, in the form of a loop, I am moving from positive to negative. So this is minus voltage across the diode is equal to 0. Okay, so what is the input? Input is plus 5 volts minus the drop is 0.7 volts is equal to VC. Okay, so what is VC? VC is 4.3 volts. Okay, we'll have to understand that VC is the voltage. Okay, voltage to which the capacitor gets charged. Okay, now even though I am applying plus 5 volts, the capacitor will not get charged to 5 volts because you have a diode. So the drop across the diode is 0.7. So it's like 5 minus 0.7 will be 4.3 volts. Okay, so during the positive half, the capacitor gets charged to 4.3 volts. So this is a very important step. Okay, unless and until you track the voltage across, the voltage that keeps developed across the capacitor, we cannot proceed further to the output side. Okay, fine. So VC is 4.3 volts. Then what about V naught? See, we are interested in V naught now. Okay, so what is V naught? V naught is the voltage appearing across the resistor, and that is nothing but across the diode, because both these lines are in parallel. Okay, so voltage across the resistor is nothing but the voltage across the diode. So what is the voltage across the diode? V naught. Okay, V naught is nothing but 0.7 volts. So during the entire positive half of the input signal, the output is 0.7 volts. So the 0.7 volts. This is during the positive half. Then what about the negative half? Okay, so during the negative half, what is the status of the diode? When I say negative, minus, plus, which means we are applying negative voltage to the anode and positive voltage to the cathode of the diode. That means the diode is reverse biased. Diode is off. So now when the diode is off, that means it behaves as if it is a open circuit. This line behaves as if it is an open circuit. That means this line has to be detached. So what we are left with? What should be the output? At the output side, the voltage is nothing but the summation of the input signal during the negative half and the voltage that was stored in the capacitor during the positive half. Okay, so the capacitor was charged to 4.3 volts. Now this 4.3 volts together with the input signal will be discharging and will be appearing across the output side. What does it mean? Well, this is plus to minus. Okay, so this is minus 5 volts of the input signal, minus 5 volts. Then what about this voltage? 4.3 volts. The capacitor was charged to 4.3 volts, but should I consider it as plus 4.3 or minus 4.3? That is very important. See here, plus to minus, okay. That means it is minus 4.3 volts. 5 volts minus 4.3 volts will be appearing across the output voltage, that is minus 9.3 volts. This is the voltage that appears across the output side. So let me just mark it. So this is the voltage that appears, minus 9.3 volts. Okay. Now as the input cycle keeps on continuing, so does the output cycle also continues. Okay, so this actually continues in a similar way. As my input continues, so does the output also continue. But the point to be observed here is about the shift. So is it a positive shift or a negative shift when compared to the input signal? Well, it is clearly observed that it is negative clamping. There is negative shift. Okay, so this is 0.7 minus 9.3. So just to verify, what about the magnitude? Is it exactly 10, lesser than 10 volts or greater than 10 volts? Because we'll have to compare it with respect to the input. The input's magnitude overall is 10 volts. In this case also it is 10 volts, 0.7 and 9.3. So overall the magnitude is 10 volts. That means the appearance at the output side of the clamped output hasn't changed. It is still the same. There is only a DC shift or clamping being observed. Well, so it's fairly simple, right? Now things may get a little complicated if I add a battery in series to the diode. So let me just add a battery to it, as we had added in the case of clippers. So here also let me add a battery of 2 volts itself. 2 volts. So this is plus minus. Right. Now again, what happens to the transition level? The transition level in this case changes. Previously it was 0.7 volts. Now it is 0.7 of the silicon diode and 2 volts of the battery. So overall the transition level will be 2.7. Okay, so instead of 0.7 I just need to change it to plus 2.7 volts is my transition level. But whether the output will start from here? Yes, it has to start from here. How? Okay, so let us just quickly verify it, right? So during the positive half, Vi is still the same. What changes is the voltage across the capacitor. Okay, because now it will be 5 minus not 0.7. Instead of 0.7 it will be 2.7. Why 2.7? Yes, 0.7 of the diode and 2 volts of the battery. So overall it is 2.7. So 5 minus 2.7 volts will be 2.3 volts. So the capacitor will get charged to only 2.3 volts. Right? Okay. Then what about the output voltage? Well, the output voltage is nothing but the drop across the diode will be the same across the resistor. So instead of 0.7 it will be 2.7 volts. Well, during the negative half, the diode is off. So what will be the output appearing? Well, it is minus 5 volts. Minus, instead of 4.3, now it will be 2.3 volts, which is minus 5 minus 2.3, that is minus 7.3 volts. Okay, so by placing a battery in this particular notation in series to the diode, the output voltage during the negative half will be minus 7.3 volts. So that has to be mentioned here, minus 7.3 volts. So again, just to verify about the magnitude, what has happened? So in this case it is 0 to 2.7 volts and 0 to minus 7.3 volts. Again, if I add them up with respect to the magnitude, it is still the same 10 volts. Okay, so my input is also 10 volts and my output is also 10 volts. Okay, so the analysis is very simple. Now there are again 4 different combinations possible even in the case of clampers. Okay, the second combination will be just reverse the polarity of the diode. Third combination, reverse the polarity of the diode as well as the battery, and you will also be getting the fourth case. So for every possible combination of the clamper circuit with respect to the diode and then the battery, you will be having different waveforms. Okay, so for 2 combinations, probably you will be having negative clamping. For the other 2 combinations, you will be having positive clamping or positive DC shift. Okay, so I hope you have understood the concept of clampers. So there are 4 different possible combinations. You can just try it out on your own. You can replace the silicon diode with a germanium diode, or you can even add an ideal diode. In this case, you can just change the battery voltages and then play it on your own, so that you will be getting different corresponding clamped output waveforms. Okay, well, so after this particular explanation, I feel that students should not feel that difficult in understanding the clampers. Okay, so they are very easy to understand. You can just use your common sense and then try to obtain the output. Okay, well, so if you have understood the concept, if you are satisfied with the understanding of the clampers, okay, so please do share it with your friends and subscribe to the channel. Thank you very much.